In our last video of notes, I told you that there were some more advanced kinds of multiplication that you could do with three-dimensional vectors. And one kind that we had already talked about was something called dot product. The name for the multiplications that you do with vectors are the symbol that you're going to see for the notation in between. So when we did dot product, we saw a dot between the two vectors. Today, we're going to talk about cross product. And whenever you're doing a cross product of two vectors, what you're going to see is the two vectors with what looks like a times symbol between them. So cross is the old word for what a times symbol is. So the cross product of two vectors produces a completely new vector. And what's special about this new vector that you create whenever you're doing a cross product is it's perpendicular to the plane that contains the first two vectors. This kind of multiplication is extremely important when you're talking about physics and you're talking about electromagnetic fields. The electric field and the magnetic field are always perpendicular to each other. So this is one of the things that really helps with understanding electromagnetic waves. If your two vectors that you're taking the cross product of happen to be parallel, then the cross product will produce a result of 0. This is one of the special features of cross product. So if you aren't sure if your vectors are parallel, take the cross product and find out if you get a 0 answer. That'll tell you definitely that they're parallel. So here's how it works. And this, by the way, only works with three-dimensional vectors, because if you only have 2 dimensions to work in, then whatever plane that your vectors are in, the cross product will be sticking out of it. So you have to have 3 dimensions for this. You have to have i's, j's, and k's. So let's say somebody gives you 2 vectors. Vector u is going to be a in the I direction, b in the j direction, c in the k direction. And vector v is going to be d in the I direction, e in the j direction, f in the k direction. So if somebody asks you to take the cross product of u cross v, the very first thing you're going to want to do is make a 3x3 matrix. So this is why I had to wait to show you vectors until after we did chapter 8 on matrices. You're going to make a 3x3 matrix, and here's what you're going to do. In your top row, you're actually going to put the 3 standard unit vectors, the I with a hat, j with a hat, and k with a hat. Even when this problem has numbers for the vectors, the top row for cross product is still just going to be ijk. Those are your unit vectors. In the middle row, you're going to put the coefficients. Those are the numbers that come in front of the I, j, and k from your first vector. So namely the a, the b, and the c. Now when this is a real vector and it has actual numbers in there, it would be the numbers that come in front of I, j, and k that are going here. And the bottom row is reserved for the coefficients for your second vector. So since v was the second vector in this cross product, its coefficients go across the bottom row. Now once you make this matrix, the cross product will be the determinant of this matrix. So here's another use for our concept that we learned back in chapter 8 when we were working on matrices. Here's another use for our concept of determinant. So remember, for a 3x3 matrix, one of the things that we found really helpful in doing determinants was copying our first 2 columns from our matrix to the right of it. So IAD is going to get copied next to this, and the second column as well, J, B, E. This way you can finish all 6 of your diagonals. So the cross product of vector u and v would be b times f in the I direction plus c times d in the j direction plus a times e in the k direction. Now those are the 3 diagonals that are going the right way, so whatever their products are, we're just adding them up. Now we've got 3 diagonals coming back the opposite direction, and those get subtracted. So it's minus b times d in the k direction, minus e times c in the I direction, and last but not least, minus f times a in the j direction. So remember, with your determinants, there's always 6 products. 3 going this way, whose products you leave alone and just add up, and 3 coming back in the other direction, and those are going the wrong way, so we're subtracting all 3 of those. When you do this cross product, 2 of your products should have i's on them. You put those together. 2 of them should have j's on them. You should put those 2 together. And 2 of them have k's on them. So when this is actual numbers, we're going to be able to collect like terms. Let's now try a couple of examples of this. So in our first example, we have vector u, which has the components 1 in the I direction, 2 in the j direction, 1 in the k direction, and vector v, which is 3 in the I direction, 1 in the j direction, 2 in the k direction. And our objective here is going to be to find the cross product of u times v. Notice the cross, the times symbol. So the first thing you need to do is make a 3 by 3 matrix. You're going to want to put your standard unit vectors, I, j, k, across the top row. Even though now these vectors have numbers, the top row for cross product is always just I, j, k. The second row should be filled in with the components, the coefficients from the first vector. So since vector u is first, we're going to use its coefficients 1, 2, 1 across our middle row. And vector v's coefficients 3, 1, 2, because it came second, goes across the bottom. Now my plan here is to take the determinant of this matrix. So I'm going to have to copy the first 2 columns, I1, 3, and the second column, J2, 1, right next to this matrix so that I can finish all 6 of the diagonals. My first diagonal is for I. My second diagonal is going to be 3j. And my third diagonal is going to be 1k. And whatever those products are, you just leave them alone and add them all up. Now we have 3 diagonals going back in the opposite direction, and these are going to be subtracted. So minus 6k. Then we have minus I, minus 1i, and then we have minus 2j. As you can see, there are 2 of each component, so we're going to put like terms together. We have 4 i's minus 1 I, which makes a total of 3i. We have 3 j's minus 2 j's, which makes a total of 1j. And last but not least, we have 1k minus 6k, which makes negative 5k. Before we proceed on to the next problem, one of the things that I want to point out here is that your answer for a cross product is always a vector. It's going to have i's, j's, k's, and what's special about that vector is it's perpendicular to both of these vectors, and it's perpendicular to the flat surface that these 2 vectors lie in. So if you could imagine that these 2 vectors were laying on your tabletop or your desktop, this vector would be poking straight up out of it at a 90-degree angle. Now the second thing that we're going to try is we're going to try taking those same 2 vectors, v and u, and we're going to cross product them again, but this time we're going to put vector v first and vector u second. So we're going to go through that exact same process. Across the top row, we put the standard unit vectors I, j, k. This time, the coefficients from vector v are going first, so 3, 1, 2 are now in the middle row, and 1, 2, 1, which are the components for vector u, are now going to go in the bottom row, 1, 2, 1. Copy the first 2 columns next to your matrix, and now let's find what our diagonals are. This is going to be positive 1i. This is going to be positive 2j. This is going to be positive 6k. Again, those are the 3 diagonals that are going the correct way, so whatever their products are, we just leave them alone. Then we have, going the wrong way, minus 1k. We have minus 4i. And last but not least, minus 3j. Putting our like terms together here for this cross product, we have 1i minus 4 i's, which is going to be negative 3 i's. We have 2 j's minus 3 j's, which is going to be negative 1j. And last but not least, 6k's minus 1k makes positive 5k. So this represents the vector for doing the cross product in this order. So the first thing that I want to point out to you is if you look at the answer that we got for u cross v, we got 3i plus j minus 5k. And the answer that we got for v cross u was negative 3i minus j plus 5k. What does it say about cross product? Well, first of all, when you compare the two answers here, you notice that they're not the same. It's not commutative. But if you look even more carefully at them, you're going to notice that the coefficients are exactly opposite. So here we had positive 3i, here we have negative 3i. Positive 1j, negative 3j. Negative 5k, positive 5k. There's actually a word for this. And it's not commutative, it's called anti-commutative. It's exactly the opposite. Now, at first, this seems a little weird, but I'm going to try to explain this in a way that makes sense. As I mentioned before, if you could imagine these two vectors laying in the flat surface of your table or your desk, and this vector would have to poke out of it at a 90-degree angle, there's only two ways you can be perpendicular to a flat surface. You can either poke out of the top half of it, or this vector is 180 degrees diametrically opposed to this vector. So what that means is the only other way you could be perpendicular to that flat surface is if you poke out of the bottom of it. So this vector is completely reversed from this vector. And that's what's called anti-commutative. And that's what happens when you reverse the order in a cross product. You get exactly the opposite vector. So all the same numbers with all the opposite signs. So the last kind of multiplication that we're going to take a look at is something called triple scalar product. The word triple refers to the fact that you're going to need three vectors for this. So 3 triple. The word scalar is talking about what kind of answer you're going to get from this. So scalar means not a vector, just a normal number. And what you're going to be doing here is you're going to be using the three vectors where two of them get cross multiplied, and then the product, the cross multiplication product, gets dot producted with a third vector. And remember, by order of operations here, things that are in parentheses are done first. So first of all, we create the cross product vector, and then we dot product, and dot product ends up giving just a scalar answer. So that's the reason why this gets a scalar answer. So this kind of multiplication needs three vectors that lie in different planes. You don't want all three of your vectors to be in the same plane because then you're going to get a zero answer for this. You could do the cross product in parentheses first and then take the dot product. So you could do this like in 2 steps. That's considered to be the long way. It would work, but it's longer than what I'm going to show you. The shortcut to doing this is somebody gives you these three vectors, u, v, and w, with these components. You can just create a 3x3 matrix, putting the first vector's coefficients, so in this case vector u was the first one in front of the dot product. You take its coefficients, a, b, and c, and you put them across your top row. You take the middle vector, in this case v, its components are going to go across the middle rows, d, e, f, the coefficients here, here, and here. And last but not least, whatever vector is last in this cross product, in this case w, its coefficients, r, s, and t, are going to go across the bottom. Now what you want to do here to find the triple scalar product, the triple scalar product will be the determinant of this matrix. And again, whenever you want to take the determinant of a 3x3 matrix, you should copy the first two columns, ADR, BES, right next to your matrix so you can finish all 6 of the diagonals. So the answer for the triple scalar product of u dot v cross w would be a times e times t plus b times f times r plus c times d times s. And that completes the 3 diagonals that are going the normal way. Now the 3 diagonals coming back the opposite way have to be subtracted. So minus r times e times c minus s times f times a, and last but not least, minus t times d times b. And again, none of these products have unit vectors on them. There's no ij's or k's. So these are all just going to be normal numbers. And at the end of the day, we're going to put these all together and just get one singular number that represents your triple scalar product. Just a number. That's what the word scalar means. So let's now practice taking the triple scalar product of three actual vectors. So vector u is going to be 3i minus 5j plus 1k. Vector v is going to be 2i minus 2j. And vector w is going to be 3i plus 1j plus 1k. So if somebody asked you to find the value of vector u dot the cross product of v and w, that means u's first, v is the middle one, w is the bottom, we're going to want to make a 3 by 3 matrix. We're going to use the coefficients from vector u across the top row, so 3, negative 5, 1. Vector v being the middle vector is going to go in the middle row. Here you have to be careful because it has i's and j's, but it's missing the k's. And missing the k's means you just have 0 of them. So the coefficients would be 2 and negative 2. And then across the bottom row, we're going to have the coefficients from vector w, which are 3, 1, 1. Okay, so to find the determinant of this matrix, you're going to want to copy the first two columns next to your matrix right here and right here so that you can finish all 6 of your diagonals. So we've got negative 6, and any diagonal that has 0 in it is going to be 0. And that diagonal is going to be 2. And that completes the diagonals that are going the right way. Whatever their products are, you just leave them alone and add them up. So negative 6 plus 0 plus 2. Now we've got 3 diagonals coming back the opposite way. So this was going to be negative 6, but it's going the wrong way, so it's minus minus 6. And that's going to be 0. Minus 0. And that was going to be negative 10, so minus minus 10. Now when you put all these numbers together, negative 6 plus 2 makes negative 4, minus minus makes positive 2, and minus minus makes, I think we get a total of 12 here. Now check this out. Let's take those same 3 vectors, vector u, v, and w, and let's take their triple scalar product in a different order. Let's put v first, and then have u be the first one in the cross product. That means v's coefficients are going to go across the middle row, across the top row. So 2, negative 2, 0. Vector u's coefficients, 3, negative 5, and 1 are going to go across the middle row. And vector w's coefficients, 3, 1, and 1 are going to go across the bottom row. And again, we're going to find its determinant here. This is going to be negative 10, negative 6. That's going to be 0. Whatever their products are, we're leaving them alone. And that's going to be 0. I was going to subtract that, but it's nothing. That's 2, so subtracting 2. And that would have been negative 6, so minus minus 6. Okay, putting these answers together, you're going to have negative 16, negative 18, minus minus 6 is like adding, so that's going to be negative 12. And so once again, you can see the answer that we get for this triple scalar product when all we did was mess with the order has the same numerical value as before, but an opposing sign. And that's due to the anti-commutative property of cross product. When you start messing with the order, you could either get 12 or negative 12, depending on who's first, second, third. Now, using these 3 vectors, there's actually 6 different permutations of who comes first, who comes second, and who comes third. Half of those permutations are going to produce a positive 12 answer, and the other half of them are going to produce a negative 12 answer. So what does this say about the triple scalar product? Watch your order. Some of them are going to turn out to be positive, and some of them are going to turn out to be negative due to the anti-commutative nature of cross product. So the last thing that I want to show you is what does triple scalar product actually calculate? You can go on the internet and find proofs of this, but I'm going to give you the short story here. The triple scalar product is actually calculating the volume of a parallel pipette formed with the 3 vectors as its edges. Now, as we just learned, sometimes that's going to turn out to be positive and sometimes that's going to turn out to be negative based on the order of who goes first, second, and third. Now, we don't want that to happen. Plus, volumes always have to be positive. the one thing that we can do to guarantee positiveness in math is absolute value. If you take the absolute value of the triple scalar product, that will be the volume. And just to show you a picture of what this looks like, you have to imagine this happening in three-dimensional space. If I give you these three vectors, u, v, and w, and ask you to calculate the triple scalar product, what you're actually finding, draw out the rest of this. It's not going to be perfect, but it's going to be pretty good. You're actually finding the volume of this three-dimensional shape. It's kind of like a prism on a slant. So you're actually finding the volume of this three-dimensional shape. Now remember, cross product could be positive or negative. We want to make sure volume is always positive, so we're going to put absolute values. You are now ready to try homework number 139, which is vector worksheet number 2.